Welcome back to Large-Scale Machine Learning. We will continue our discussion on incremental machine learning. So previously we talked about how we can use gradient descent type of algorithms to implement incremental learning, and basically gradient descent type of algorithms are what we typically use in a neural network. And we talked about how we can use the SGD classifier and SGD regressor, and that basically implements a one layer neural network. And by adjusting the loss functions, we can actually implement various algorithms such as logistic regression, regression, and support vector machine type of algorithms. And now we are going to take a look at some other incremental learning algorithms that's supported by scikit-learn, besides the ones that we can implement using gradient descent. So this particular slide shows how you can actually train a large data set incrementally. So we can train the model on a large data set one batch at a time. So many scikit-learn estimators implement that partial fit method, which enables us to do incremental learning in batches. So you first create the estimator using the classic way of generating it from the class. And then once you have the estimator, you can call the partial fit function with the first batch of data, the first chunk of data. And later on, if you want to continue incrementing, you want to continue doing the training, you call partial fit again with the next batch of data, and so on and so forth. Of course, you can put this in the loop and just cause it to actually iterate through different batches of data. Now this can be combined with another library called Dask, and Dask is a parallel execution library that's meant for distributed machine learning. So it does have an extension called Dask machine learning, Dask ML, and within the Dask machine learning, there's what we call an incremental meta estimator. So it's an estimator that automatically makes use of scikit-learn partial fit over the data structure called Dask arrays. So Dask arrays are very much like pandas data frames, but they support the chunking of the data. So instead of storing one single gigantic pandas data frame with a billion rows, right, 1,000 million rows, we can divide that into chunks, right? So every single chunk within the Dask array may be a panda data frame equivalent, where it stores 1,000, maybe 10,000 rows, and then many of these chunks of 10,000 rows makes up the entire data set. So Dask has this mechanism that enables us to scale up the speed of pandas data frames. And since pandas data frame can be converted into NumPy array and then called within the fit function, we can use the Dask ML incremental meta estimator to basically call fit function one chunk at a time, or one part of the Dask array at a time. Scikit-learn handles all the computations, right? So we actually call scikit-learn's partial fit from within the Dask ML, while the Dask library handles the data management, right? The chunking of the data, loading and unloading it from memory will be handled by the Dask, and the algorithm implementation is actually called using the scikit-learn itself. Now this allows us to really scale up to very large data sets and also distribute it across multiple machines. So later on we'll talk about how Dask can do this distribution, spread the load for the learning computation over multiple machines. This part here, we are mainly talking about Dask's role in calling the scikit-learn estimators that implement the partial fit and able to basically chunk the data instead of using one gigantic pandas array. So this allows for scaling for large data sets distributed over many machines, or to data sets that do not fit within the memory of a single computer, all with a familiar workflow. So it's very similar to what you do with pandas and scikit-learn on a standalone basis. Now, just that with the Dask libraries, we are able to scale it up across multiple machines, a cluster of workstations, instead of just one single machine to run your training operation. So here are a list of classifiers that support incremental learning in the scikit-learn. So besides the SGD classifier, we have some that belong to the naive Bayes family, the multinomial and the Bernoulli version. We notice that the linear model perceptron is also supporting partial fit. No surprises here, since perceptron is basically like a simple linear one-layer neural network. It's very similar to SGD classifier, except the activation functions are different. And then we have another one, which is we'll talk a little bit more about this later on, something called the passive aggressive classifier. There's also a regression version of this as well. So this particular model algorithm is actually suited to larger data sets. So we're going to spend a bit of time to talk a little bit more about this. It's actually very similar to the perceptron. And then finally, the multi-layer version of the SGD classifier, the MLP classifier, also supports partial fit. One thing to note about classification is that even if the feature selection part, feature extraction part of your pipeline is able to cope with new attributes or unseen attributes that are appearing in the later batches of data. Remember, in partial fit, we are training it batch by batch rather than all at once with the entire data frame. But the incremental learner alone, it may not be able to cope with this. In other words, all these estimators, right, they may not be able to cope with new unseen classes. I mean, unknown class labels that have not appeared yet. So it is important that you specify all the possible classes in the first partial fit call to take into account this effect that the incremental learner may not have the ability to cope with new unseen classes if it doesn't appear in the data, in the first batch of training data. So here are the list of regressors. The list is somewhat shorter that support partial fit. We have the SGD regressor, which we have talked about previously, and then the newer version, the passive aggressive regressor, and the MLP version, similar to SGD. MLP is the multi-layer version of the regressor, and like all neural networks, it can support partial fit. So in this slide, we have a little bit more detail about those passive aggressive classifier and regressor that we mentioned earlier, and it is just a basic overall picture of how these passive aggressive algorithms work. They are called passive aggressive algorithms because there's a passive mode and there's aggressive mode. So in the passive mode is when the prediction is correct. So if the model predicts the result correctly, we keep the model and we don't make any changes. So it passively accepts the model as it is, and the data in this example is not enough to cause any change in the model. Now in the aggressive mode, if the prediction is incorrect, then we make changes to the model, and that is some of the changes to the model may actually correct for the incorrect prediction. So it toggles between these two modes depending on the results of the prediction. Now passive aggressive algorithms are generally used for large-scale learning, so they are tuned for this type of problems. So this is why they are going to be very suited for large-scale machine learning. It is one of the online learning algorithms, which means that we can incrementally add data to it. It's not just a batch mode data. Now, passive aggressive algorithms are somewhat similar to the perceptron model. Remember, I said that it's very similar to neural network, right? Perceptron model, because they don't require a learning rate. Okay, so there's no learning rate in the perceptron as well. However, they do include a regularization parameter that you can tune, right? So they can remove additional complexity that is causing the model to overfit and improve the generalization. So this is what regularization generally does, and there's a parameter to introduce regularization into the algorithm. And if you are interested to find out more about these algorithms, they're actually fairly new, right? You can actually look at these two articles, right, on this passive and passive aggressive algorithms, which is an improvement over the simple perceptron model. Then for unsupervised learning, we do find that we have clustering algorithms that can also support the partial fit. So this is quite interesting because not only supervised learning algorithms like uh, classifiers and regressors, but also unsupervised learning. The k-means has obviously the normal fit function, but this particular version of k-means, the mini batch k-means, it also supports the partial fit function, so you can do incremental learning. Another algorithm that supports the partial fit in the clustering family is actually the Birch algorithm. So these two are the ones that can support partial fitting, which means that they can actually do incremental learning over, if you're doing clustering over a very large data set, these are the two go-to algorithms. Now here is a set of incremental learning algorithms that are actually related to the features rather than just a pure learning algorithm. So the first set is what we call dimensionality reduction algorithms, and these are actually unsupervised, a type of unsupervised learning. So the first one that we have is the mini batch dictionary learning, and then we have another very well-known dimensionality reduction algorithm called the principal component analysis, or PCA. Now PCA is normally operating over the entire data frame, but if you have a very large data set, it might not be possible for you to run it, the PCA with just this huge data set, this huge data frame inside the memory. So they have actually implemented an incremental version of the PCA. This allows for partial fit, so you can actually do the PCA computations a batch or chunk of data at a time. So this is very useful, right, to enable extend the PCA beyond just smaller data sets into very, very huge ones. Then we have the latent Dirichlet allocation, or LDA. This is not the same as the linear discriminant analysis, or LDA. So this particular one, latent Dirichlet, is meant for text analytics or NLP type problems. And as before, normally the latent Dirichlet allocation operates over the entire data frame, but we also have a partial fit function implemented in it, so that we are able to perform this function without having to have the entire dataset loaded in memory at the same time. So this decomposition algorithms are very useful because of the partial fit. They can now operate over a very large dataset instead of just a smaller one. The PCA actually is the same algorithm as the normal PCA. It's just that this particular implementation of PCA supports the partial fit. In terms of the mathematics and the algorithm mechanism is the same. It's just that this particular implementation, we have included the partial fit function in it. Now, those below here, these are not unsupervised learning algorithms, but I've included them here because this also have to do something with the features. So one of the common things that we need to do with features for many machine learning algorithms is to make sure that we scale them to similar range of values. Because one of the problems with many distance-based machine learning algorithms like k-nearest neighbor and even support vector machines, which depend on the distance, is that they are sensitive to the scale or the range of values in each of the features. So what happens is that the values that are larger, they tend to dominate over the smaller range of values. So if you have an elephant in the room, the elephant will basically just dominate the entire scene, and all the small mouse-sized values will be ignored. So this, to prevent this from happening, we need to normally scale the value. So there is a number of scalars here. So one is the standard scalar that uses the standard deviation. So it sort of uses the bell curve of the data, and then it scales it down to a range of values that's between -3 to 3 standard deviations. So this actually works very well with bell-shaped distributions, and it preserves the distribution in terms of the variance. So this is good if you're going to use it together with PCA, because PCA it depends on the variance. So if you distort the variance, the PCA will not be as effective. So standard scaler is used normally with PCA. But this particular implementation of standard scaler, besides the normal fit function, also supports partial fit, so that we can actually do the standard scaling chunk at a time over a very large data set. The min-max scaler is one that takes the minimum and maximum value and then divides it by the range of values. So it scales everything down to 0 to 1. And this is again something which we would normally do for example, image processing in a neural network. And it's quite useful because this will allow us to basically now support very large data sets, since this also supports the partial fit function. Lastly, we have the max absolute scaler, and this is also another common scaler that we use to support large data sets as well. So here is a quiz for you. What class of problems require incremental learning? Is it A, memory bound, B, CPU bound, C, all of the above, or D, none of the above? So pause a minute and think of the answer before you move on. And we come to the last slide, so thank you for your attention.